somebody confirm me from the online fellows? Can you hear me? Thank you. The check-in code for online people is 38836. Alright, any questions from our previous discussion? And I mean about lecture, not about practical or tutorial. Are there any questions from what we were studying last week in our lectures? So last week we started aromatic compounds, right? We looked at these four qualities for the compounds to be termed as aromatics, and we saw that all four of them should be fulfilled for any compound to be called aromatic. If one of them is missing, then they become non-aromatic compound. Well, the obvious stress was on the Haskell rule, because 4n plus 2 pi electrons make what is required for aromatic compounds. Well, 4n pi electrons actually make them anti-aromatic compounds, right? The focus of this chapter is on aromatic compound. The most important aromatic compound was, of course, benzene. We did talk about it, its structure, right? Then the bond angle, bond strength, bond order, these things we discovered. This was the molecular orbital structure of the benzene. Just like any other alkenes, they are also trigonal planar in simple words. But of course, they are nothing like alkene about their chemical and physical properties. Later on, we talked about some PAH, right, such as naphthalene, anthracene, and so many others. Why they were important, right? So they are very common environmental pollutant. They are threat to several human or like living organisms. That's why it's important to monitor and not use them, right? We had some sort of similarities between the structure of PAH and simple carbon allotropes. We just kind of looked at it, that what are the similarities, how the structure of PAH resembles with the allotropes of carbon. Right, then we looked at some other examples of fused heterocyclic compounds which might not be only hydrocarbons, because PAH are polyaromatic hydrocarbon compounds, right? But then in these cases we saw that other heteroatoms would also be part of the fused ring. They are still considered aromatic but not truly, because the heteroatoms has a different size, so they skew the structure a little bit. But for the sake of argument about this course, we will consider them aromatic compounds. This is a bit advanced. In like modern chemistry, heterocyclic are not said as to be true aromatic compounds. But at basic level, yeah, they are very much aromatic. The only difference is that heteroatom makes the structure a little bit non-planar, a little bit only. But probably I shouldn't say that. So just consider them that they are aromatic compounds to avoid any confusion for the sake of this course, yeah? Right, I think this is where we left last week. So, any questions? The criteria is understood, right? For aromatic compounds, we will not be having a separate tutorial section. The only tutorial section that we will have now, which is next week, would be about stereochemistry, which probably will start today. But this does not mean that you will not get practice questions for alkynes as well as aromatic compounds. I will upload them on eLearn for your practice, and later on I will also sort of is the answer. Of course, you can reach out to me before the end of 7th week. I'll be happy to discuss them with you in person or in groups. But then the only other tutorial which I will be conducting would be in the following week, and that would be about biochemistry. Right? So alkynes and aromatic compounds, there wouldn't be the separate tutorial sections. Yeah? Right, so something about their physical properties is that since they are high in percentage of carbon as opposed to alkane, alkenes, and alkynes, so because of that, when you burn them, you will get the formation of soot, which is just a fancy word for black colored smoke. And this is because carbon is essentially coming from coal, so high percentage of carbon makes them burn with the soot, right? Besides that, the melting point, which we generally see for all classes of compounds, is a bit higher as opposed to the other relevant functional groups. And the reason for this is that most of the aromatic compounds are actually benzene or benzenoids, right? So their structure is hexagonal, which just packs with each other because of the symmetry quite well, which gives the strength to their solid state structure, and therefore their melting point are generally a little bit high. The boiling points, of course, they are about their properties in liquid state, right? So in liquid state, the polarity of structure takes very high importance. And I know that we haven't studied orthometapara yet, but different structure of aromatic compounds may have difference in their boiling point because of the formation of high poles or let's say just dipole moment. That term is well understood, right? Or just the formation of poles. This has something to do with the unsymmetry of the structure, which we will see later today. Right, density, all organic compounds almost are less denser than water, and of course, because of their high percentage of carbon in their structure, they are quite insoluble in water. Right? So these are some of the other very common aromatic compounds which are not directly benzene, but they are derivatives of benzene. What I am showing you here is that you may need to remember some of these names. Phenol, for example, you have to remember because that will come very useful in the IUPAC nomenclature of aromatic compounds. Toluene, not that important. If you can remember, perfect. If not, then it's fine because simply methylbenzene. So in IUPAC it goes by methylbenzene. Aniline also okay, I guess. Benzaldehyde, very important. Benzoic acid, very important. And probably aniline is also a little bit important. So these 4 or 5, if you can remember, that will really be helpful in your nomenclature problems, which we will see shortly. So what's the difference? That when benzene ring has hydroxyl group, it's called phenol. That's just the name. There's no way around it. We'll have to put this in our memory, unfortunately. Toluene, not so important, so I'll just cross that off. Aniline is when amine group is present on benzene. While aldehyde makes it benzaldehyde, and carboxylic acid makes it benzoic acid. This is also very, very important, as you will see shortly. Right. So these are some of the common benzene derivatives when they only have one functional group. You see all here is like one is benzene ring, and beside that we have one functional group. Here we have carboxylic acid, aldehyde, ketone, and so on and so forth, right? So what happens when we have 2 substitutions on benzene? Then these neighboring groups are called ortho. So technically 1, 2 positions, if the groups are present beside each other, then they are called ortho. If there's a gap of 1 carbon between them, they are called meta, or simply 1, 3. And then when they are opposite to each other, then they are called para in common words, or in numbering you can simply call them 1, 4. So when we will give IUPAC nomenclature, we can use numbering as well as ortho-meta para. Both of them are kind of acceptable in IUPAC nomenclature, as we'll see later. Right, but of course, the common names don't use the numbering, so we use ortho, meta, and para more commonly in the common name. Here are a few examples. So we have these two chlorine present next to each other, right? So they are called ortho dichlorobenzene. Right? Dichlorobenzene, as it has two chlorine, and ortho tells that both of them are next to each other. It doesn't matter that first group should be here. If one chlorine is here, one chlorine is here, then also they will be called ortho, right? Ortho dichlorobenzene. Similarly, in this case, we have 1,3 arrangement between the two groups, so it's called meta-chloroperoxybenzoic acid because it's CO3H. It's not carboxylic acid. That's just another functional group. But what is important to note here that when they are in 1,3 relationship with each other, then we have to put this M for meta. Right? Here we have para-nitrophenol. We really don't need any other thing. It just simply tells that there's a phenol, and at para position we have the nitrogen. Right? Right, so when we have 3 groups, then what happens? So one thing I think you did not notice in the previous example is, when the groups were same, then no problem. But when the groups are different, then which one we include in the name as the main compound and which one we put as a substituent. Meaning, just to say as we used to say, alkyl group as branches in our previous IUPAC practice sessions, right? So in this case, how do we decide that this would be the last part of the name and this would be put as a substituent? Or here, this would be put as the main name and this group will be put as the substituent. So to answer that question, a little bit knowledge of function groups will be helpful. So the functional groups which are more oxidized, they generally get high preference in naming them. And this rule will also be standing just like it is standing here in the cases of when we will proceed with other functional groups later in this course. So generally speaking, which is true for multiple functional groups containing compound is this, that when 2 functional groups are present, so the one which is more oxidized will be given high preference in the nomenclature system. So here, this peroxybenzoic acid is obviously very, very oxidized because of so many oxygens. So you see that the main name is actually peroxybenzoic acid. And here phenol is also quite oxidized as opposed to nitro group, so nitrophenol. Right? We might have called it, something else as well and given more preference to nitrobenzene and then said that hydroxyl is present here. But because of their oxidation state, we prefer it this way. So similarly, this happens in when 3 groups are present. So they could be at 1,3,5 positions, 2,4 positions, or 3,5 positions, all based on what is the main functional group in these compounds. So here, nitro and hydroxyl. So of course, hydroxyl including the benzene ring becomes phenol, and then we simply put the positions of the other 2 nitro groups. In this case, carboxylic acid is the important group, so this whole becomes benzoic acid, and then we simply write hydroxyl group as them by themselves, right? So when we are deciding that this will be the main group, then you see that these hydroxyls are still put as hydroxyl and not as phenol. The molecule cannot be benzoic acid and phenol at the same time. So one of them will need to be put as a main group, and then the other group will be put as, the simple substitution. This makes sense, right? And how do we decide? Based on their oxidation number, oxidation state. So generally speaking, carboxylic acid is like at the top of the oxidation chain, while methyl is at the lower end of that spectrum, right? Okay, some of the more examples here. These are the common names. There's no point, I think, to remember them, but just take the examples of their name and it will make more sense. Dimethylbenzene, no problem. No one is more important. Both are methyl. Here, trimethylbenzene, 2-methyl benzoic acid, and 4-methyl phenol. So, of course, between carboxylic acid and methyl, carboxylic acid takes the lead. Between methyl and hydroxyl group, hydroxyl takes the lead, right? So when we will be doing the nomenclature, you will sometimes be confused in these two groups. So this slide defines that what is the difference between phenyl and benzyl group. So phenyl group is when the benzene ring is directly attached as a substituent somewhere, and benzyl group will be the one where we have one extra carbon as a connecting atom to the main chain, besides the benzene ring, of course. So both of them have benzene, right? But in phenyl, the ring is directly attached. And in benzyl group, there is one carbon in between the benzene ring and where it is actually attached. So do not miss out on this carbon, and this is carbon. You cannot call this ring as phenyl ring anymore, right? And the examples are benzyl bromide, benzyl alcohol. In both cases, you can see that we have that CH2. Otherwise, if we didn't have this CH2, then this would be bromobenzene. If we didn't have this CH2, then this will be single phenol, right? Okay, let's talk about the chemical properties of benzene, which is the representative for us about the aromatic chapter today. So when benzene was reacted with bromine in the presence of iron bromide, the reaction was performed in carbon tetrachloride as a solvent. We didn't get the addition product as we would expect in the case of carbon-carbon double bond. So now you know that carbon-carbon double bond can really do addition reactions with bromine, right? And then carbon-carbon single bond, they can do substitution reaction as we saw in the case of alkane, the free radical mechanism, right? But in case of benzene, we got the substituted product and not the addition product. So what happens there, or what type of reaction is this? So this is an example of electrophilic aromatic substitution reaction, which are the characteristics for aromatic compounds. Previously we saw the 4 criteria, right, for the compound to be aromatic. Arguably you can add this one as 5th, because all aromatic compounds, they do electrophilic aromatic substitution reaction, which is quite unusual for a compound bearing so many double bonds. Because if you add halogen to double bond, what happens? You have done this in practical lab as well. So we had bromine and we added in alkane, color didn't change. We added in alkene, the color changed directly, which means that the bromine did the addition reaction with carbon-carbon double bond, right? It should be like this here as well, no? But aromatic compounds don't go to that route, and it has everything to do with the mechanism of this reaction. So just like bromine, we can have the electrophilic aromatic substitution reaction of benzene with so many other things, such as chlorine, right? And then we can do nitration as well to introduce the nitro group on benzene ring. And nitration is generally done when benzene ring is reacted with nitric acid in the presence of sulfuric acid. We can do sulfonation as well when we treat sulfur trioxide in the presence of sulfuric acid to the benzene, and we get benzene sulfonic acid. Right, these two common names you might have heard before if you have studied any organic chemistry. but if not, never mind. We can also do alkylation of benzene ring, and that reaction is called Friedel-Crafts alkylation. So Friedel and Crafts were the two scientists who discovered this reaction for the first time. What happens here is that benzene reacts with any alkyl halide in the presence of aluminum chloride. So you get the alkyl part of the alkyl halide as a substituent on your benzene ring. Similarly, if you have an acyl part, so acyl can also be added just as a ketone to benzene ring. So these two reactions are called Friedel-Crafts alkylation or Friedel-Crafts acylation. Right? So all of them are simply the example of electrophilic aromatic substitution reactions, which is quite unusual, right? As we saw from the halogenation reaction. So the mechanism of this reaction just looks like this, that your electrophile will be attacked by the pi electrons of benzene. It doesn't matter if it needs to be this one, it could be any of the three. And then we have the electrophile attached to the ring, and then following the positive charge, the electrons will move towards the positive charge to fulfill that deficiency of electrons. And finally, the proton will be eliminated, giving away the pair of electrons to fulfill these lack of electrons. And as a result, we will have reattainment of the aromatic ring, benzene ring, and in doing so, we will have substituted the hydrogen with the new electrophile. So all these reactions which we saw in previous 2-3 slides, meaning bromination, chlorination, sulfonation, or Friedel-Crafts alkylation, acylation, they all proceed the same mechanism. Right? Any question here? Is it tricky a little bit? So it is quite important for your understanding of organic chem as well as for your exam to some extent. Right? At least two things you must remember. First, that aromatic compounds, they do electrophilic aromatic substitution reaction. If the example is given to you, you should be able to identify that what type of reaction is going on here. Second, to some idea, these all steps are just recurring. It doesn't matter. If you are asked to draw the mechanism, you can do it in single step as well. But here I'm just trying to show you that electrons will be flowing in the direction of where they are needed. Right? So electrons will always go to the positive charge. That's what we are doing here, and that's why we make so many steps which don't really mean anything. Because benzene ring is symmetrical, right? So where the positive charge is generated is not important when there's only one group. When there are more than one group, of course, it becomes very important, which we will see shortly. So is this clear? Are there any questions on the mechanism or this unusual reaction of benzene compounds? All good? Right? Everything okay? Perfect. Right, the other types of reactions of halogen compounds are oxidation and hydrogenation. So oxidation is also very, very important for benzene compounds, because regardless of how many carbons are present there, in whatever form, single bond or double bond or triple bond, or as long as they are not other functional groups, if they are hydrocarbons of any sort, when you will react those compounds with KMnO4, which is a strong oxidizing agent, you will always get benzoic acid. Right? So how cool is that? If you need benzoic acid from any place, you can start with any of the substituted benzene compounds which carries carbon chain on them. And this type of example we did see in our tutorial last week as well, if you remember. So you were probably thinking at that time that it is about the cleavage of carbon-carbon double bond, but really it was about this, that all the carbons which are present on benzene ring will simply break off and be converted into benzoic acid. Right? Right. also quite tricky because this was also kind of suggested during that tutorial class that if you want to reduce these carbon-carbon double bonds, you have to use a specific catalyst, which is platinum oxide. While if you use palladium, that will not be able to reduce these double bonds of benzene ring. So we need a bit stronger of the catalyst, which is platinum oxide. Okay? So if you need to convert something from something, this information will be tricky. If you don't write the catalyst and you simply write hydrogen for your exam, for example, you might not get the full point. I will give you still the points if you just write platinum and not platinum oxide. Because then I would imagine that you know that palladium cannot do it, but platinum in any form will be able to do it. Does this make sense? So what I'm saying is that you should try to associate platinum with benzene ring and palladium with non-benzene carbon-carbon double bonds. Right? Thank you. Yes. And we'll have a side product, of course, based on how many carbons were there. If there were 5 carbons, then benzoic acid is just taking 1 carbon, right? So the other 4 will be converting into carboxylic acid as well. It will be a cleavage. So the first carbon will be cleaved as benzoic acid. That's what this reaction means. Thank you, Victor. Right, so this brings me to the most important topic for this chapter, which is activators and deactivators. So when we have one functional group already present on benzene ring, doing the second substitution reaction will impact both things, the rate of reaction as well as the orientation of the second incoming group. Right? So this topic in some textbook is also known as orientation in benzene ring. Or is it called orientation in disubstituted benzene ring? Yeah. As it just simply translates the whole topic by the title itself. But simply what I am trying to show you here is that when any group is already present on benzene ring, then these two positions, meaning ortho and para, are affected by the presence of that group. Now that group could be one of these categories. Either that group is an electron donating group or that group is an electron withdrawing group. So when electron donating group is present on benzene already, right, then these positions are activated. And if electron withdrawing group is present, then these positions are deactivated. Right? Why, we will see shortly in the next few slides. But you might be thinking that what happens to the other two positions, or I should say just one position, because this is meta, right? If you go here or there, in both cases it's meta. So what happens to meta position in electron donating and withdrawing cases? So of course, if these two are activated, then this will be the one that will be deactivated. And if these two are deactivated, then meta position will be activated. Right? So what is important? This slide simply tries to help you to remember that where does it matter the most. So it matters at the ortho and para position. If you can remember this, you will have very easy time for the next few slides. Now the reason for this is, again, the mechanism of the reaction. So we have the 3 possibilities, right? That if a group is already present as Y, then the second incoming group would either go to ortho, to para, or to meta. Right? Now if you simply move electrons after putting that group in those positions, let's talk about the ortho position first. So, these electrons will capture the electrophile is attached at the ortho position. That will generate a positive charge here. To remove this positive charge, these electrons will move there. So now positive charge will come here. Then these electrons will move here. So the positive charge will come here. So as you see that the positive charge is being generated at only meta positions, while the first position is not that important. You can forget about it. In case of para attack, again we will see that the positive charge will be generated at meta positions. Right? So we can see that ortho and para are kind of similar in terms of the mechanism. While if we put the second incoming group at meta position, then we will see that the positive charge will be generated at ortho and para positions. Right? No rocket science going on here. Same stuff. It's just the movement of electron to the next atom. Right? We put at ortho. In this case, we put at para. In this case, we put at meta. And then we move electrons to see what is happening. So when we move electrons, what do we find? That in ortho and para attack, we get the positive charge generated at meta position. And in case of meta attack, we get to see the creation of positive charge at ortho and para position. This is what I meant when I was saying that these two positions are most activated. So now we can see, right? In other case, when they are activated or deactivated, then the only other position will be the opposite of that. If it is activated, then the other position will be deactivated. And if it is deactivated, then the other position will be activated. Right? So these two are grouped together. That's why deactivating groups are meta directors. Meaning that if a deactivating group is present on benzene ring, the incoming group would like to go to the meta director, to the meta position. Right? And of course, activators will be ortho and para directors. So they will direct the incoming group at either ortho or para position. Let's look at few examples and then it will be easier to realize. Now, while we are talking about deactivators, so their identification is that, of course, they are electron withdrawing groups. So, just consider the name. What type of reaction are we studying at the moment? Electrophilic aromatic substitution, right? That's the mechanism that we are studying right now. So, if we want to increase the rate of reaction, we have to increase the nucleophilicity of benzene, right? Or if we want to slow down the reaction, then we will have to decrease the nucleophilicity so that it will not attack the electrophile. Because electrophile is the thing which is coming on benzene ring, right, to start with. Correct? So electron donating groups will increase the nucleophilicity of benzene ring, and electron withdrawing groups will take away the electrons from benzene ring, then it will not be a good nucleophile anymore. So it will not be attacking the electrophile so easily. Does this make sense? Right? No? So still heads that I cannot tell anything. Not nodding, not doing anything. No? Don't understand? What you don't understand? Which part? The direction, right? So, what reaction are we studying? Electrophilic aromatic substitution, right? Meaning that we have benzene and it will get a new electrophile. That's the overall outcome of the reaction. Now, if you want to facilitate this reaction, if you want this to happen faster, what do we need to do? We need to increase the electron flow towards benzene ring. Then it becomes a good nucleophile so that it can attack the electrophile easily. This is what I'm saying, that when an electron donating group is present, then the reaction will be faster. And if you want to slow down the reaction, then we need to withdraw electrons from benzene ring, make it a bad nucleophile, so that it cannot attack the electrophile so easily. So this is what electron withdrawing groups do. Right? So always in any reaction, mechanism of reaction you can understand if you understand the flow of electrons. So electrophile is coming to benzene ring. Benzene is a nucleophile. You want to facilitate, increase the negative charge to benzene ring. You don't want to facilitate, take away the charge from benzene ring so that it will not react with the electrophile. This is what we are talking about here. So here are the examples of almost all the functional groups which are kind of important about different examples. These are some of the cases of extreme deactivating groups. So deactivating groups are also meta-directing. That's what we saw in previous two slides, right? And these are the groups which are activating, and they also happen to be ortho-para-directed. So you will see the similarity in them, that all of them have extra electrons, so that they can put in some more electron push to the benzene, make them more nucleophilic, so that they can easily attack the electrophile. While here, you will see that the presence of these multiple bonds or positive charge is present, which will withdraw electrons from the benzene ring. So benzene ring has 3 pi electron pair, right? So they will be taken away by these groups. Hence, they will deactivate this reaction. Correct? Because this reaction is electrophilic aromatic substitution. It requires the flow of electrons for attacking on the electrophile. Right? Then we have few groups which are only halogens. Just one group, I should say, just different atoms here. They are in the middle of this spectrum. So they are actually ortho-para-director, but they don't activate this reaction. They slow it down. And we will see at their mechanism to understand all the 3 cases. Right? So here is the comparison between an electron donating and electron withdrawing group. So amine is an example of electron donating group. Nitro is a perfect example of electron withdrawing group. Why? Because it has a positive charge next to benzene ring. So it will definitely suck off all the juice of electrons from benzene ring. Correct? While amine has that lone pair, so it will push more electrons towards benzene. So when this will push electrons towards benzene, then electrons will continue to rotate to generate an extra negative charge. And what do you notice? That this negative charge again is produced only at ortho and para position. So when this negative charge is produced at ortho and para position, that's where they will attack on the electrophile. So hence, electrophile would only be coming at ortho and para position, because they are the ones which are getting high electron density because of the push of the electron donating group. Right? Is this making any sense? Why this is happening? Because amine can push electron toward benzene, and in doing so we are generating a negative charge at ortho and para position. So electrophile is positively charged. So technically that's only where it would want to go, because here we have the negative charge, electrophile is positive, we can have electrophile at here or there. So ortho-para. Right? The other case is nitro. Nitro has the positive charge, so it will withdraw electrons away. Right? In doing so, we will be generating a positive charge. Again, the positive charge is only generated at ortho and para position. But can an electrophile come here now? Because it is already an electrophile carrying a positive charge, meaning that no more electron density here. So electrophile will never come here. Positive will repel each other. So where else the electrophile can come? Only the meta position. And therefore, electron withdrawing groups are meta-directors. Right? Can someone just explain this in simple words if my words are a little bit difficult? What do you think, man?
Basically, since that last time we roll
because positive charge is being generated on those positions, right?
So only one is the meta position.
Correct? Are you able to see that? This position does not carry a positive charge, so electrophile can still come here. And therefore, electron withdrawing groups can only be meta-directors. While the opposite of this is true in the case of electron donating group, because we are actually generating a negative charge in those positions. So in these cases, can an electrophile come at meta position? No. If we have an electrophile, of course it will go to the negative charge. Right? Understood? Thank you. Right, if you look at the practical applications, what difference does it make in the case of rate of reaction? Because remember that meta-directors are deactivators and orthopara-directors are activators. So, example of a meta-director which is nitro group. So, if nitrobenzene reacts with nitric acid and sulfuric acid for another nitration reaction, then the second nitro group can come at ortho, meta, or para. But you see, para is like almost nothing. But ortho is also not that much, but at least some. Meta is the one which is the predominant product in this case. Right? 93%. And you also can notice one thing, probably you might have missed that nitrobenzene is doing the same reaction, but it requires 100 degrees temperature now. While when we had just benzene, the reaction could happen at room temperature. This tells us that this reaction requires extra energy, which suggests that nitro group is deactivating this reaction. It's not favoring this reaction anymore, as opposed to benzene. Right? You can see that nitration previously we could do at room temperature. Yeah. While when nitro group is present, the reaction is not favored anymore, so we need to supply extra energy. And of course, the predominant product is meta. Right? So it's like 100,000 times slower than for benzene. Experimental data. This is all experimental data. Right. So now we have seen the cases of electron donating and electron withdrawing group, which were clear at the opposite spectrum of the activators and deactivators, right? And then we saw in that spectrum that halogens were in the middle. So what happens in the halogen part? So halogen is a special case. Since halogen atoms are not clearly an electron donating or withdrawing group, they do have quite high electronegativity, so they generally should take away the electron from benzene ring. But then benzene ring also is not that easy of a thing which will give away electron because of the stability of the resonance of the structure. So what happens in the case of halogen is that halogen in these reactions does not put any inductive effect on the ring. Because if you talk about inductive effect, then any attack we will have positive charge opposite to the carbon which is attached to the halogen atom. So that would be very, very unstable because halogen needs electron to pull towards itself. That's the electronegativity definition, right? So if we somehow get a positive charge next to halogen, that wouldn't make any sense, right? Because halogen is electronegative. How can it have an electropositive carbon next to it? So instead of having an inductive effect, which is generally every time for halogen, in these reactions, halogen displays its resonance effect. So it just now is doing something unusual, but it does to proceed the reaction and give away a pair of electrons to the carbon to restore the aromaticity of the benzene ring. Because if we put the group on any position, it doesn't matter, this carbon which is next to halogen will always get a positive charge. And therefore we cannot use the inductive effect of chlorine and can only use the resonance effect, meaning the electron pair will be moving like it does for oxygen and for nitrogen. This is what it does, right? That the lone pair can go towards the next atom because of the presence of this positive charge. And why it is doing all this favor? Because of the stability of benzene ring. So hence it is called the resonance effect, because the structure of benzene has the resonating carbon-carbon double bond and carbon-carbon single bond, right? So in this case, ortho or para attack is more suitable because chlorine is ready to give away the pair of electrons in only the case when positive charge is present next to it. If we do meta, then positive charge will not come here, right? Then the positive charge will come either here or there. So this tells that halogen atoms are deactivators because the conditions are not favorable, but the only favorable product for them is to put the next group at ortho and para position, and hence they are ortho-para directors. So all other deactivating groups are what? Meta directors, and all other activating groups are what? Ortho-para directors. But halogen is the only exception. For example, where the group is deactivating because of its inductive effect, but ortho-para director because of its resonance effect. Right? Are you able to see this as an exception? Because we hardly see halogen giving away its electron. It has so high electronegativity that it will always pull off electrons from it. Right? Okay. This is what type of question you can expect in your exam from this orientation topic. Devise a synthesis of para-nitro tertiary butyl benzene from benzene. So your starting material is benzene, and you are to make para-nitro tertiary butyl benzene. So there are two things you can do. First, you can do alkylation reaction to put the tertiary butyl group on benzene, or you can do nitration reaction to put nitro group on benzene. The next step would be, now it has one of these two groups, right? Now to put the other group, you will do the successive reaction. Now one of them is suitable because of the activating and deactivating properties and ortho and meta director properties, but the other one will be very unfavorable and will not give you the required product. So the required product is para-nitro. So if we put nitro first, now nitro is a meta director. The next alkylation product will give us meta substituted final product. So for this reason we have to do alkylation first, because alkyl benzenes are actually ortho-para directors. So you will get the nitro group at the right position. Are you able to see the difference between these two? If you do this, this does not only slow down the reaction because of the deactivation of nitro, it also will not give us the right product. Because having nitro first on the benzene ring means that the next incoming group will go to meta position, which is not your question. Your question is to make the para product. So the sequence you will have to probably consider when making multiple step synthesis about benzene compounds. Although the reaction mechanism and all these steps are same, but because of the limitation of the deactivation and activation, or in other words, orthopara and meta directors, you have to look at the sequence that which one gives you the best product. Is it okay? I think you can use a break right now. Right? Let's take 5 minutes then. We'll start at 6:04. Any of this is here. Answer it, Ruby. Are you here? Okay. Where are Ruby?
That's not him. It's fine. That's so fair. 나는 예쁜요. 움직임. Wait. 내가 점수 너무 많네. He's on his side.
Right, in the meantime, are there any questions? What we have been discussing so far? We have finished the chapter for aromatic compounds. This is the negative charge. So negative charge they will go here, and these electrons will go here. This double bond will convert to negative. Now we have a negative charge here. So this is negative charge here. What we see here is a negative charge which favors so we can generate negative charge. Alright, breaks is over. Any other general question? So with that we have concluded the aromatic compounds chapter. As I said earlier, I will upload the practice questions for your practice. You can do them in your own time. I will upload the answer right away because we will not be discussing them in the tutorial sessions. So you'll have the guide to work with as well. Right, so the next topic is stereochemistry. The class objectives for a stereochemistry chapter will be to understand why stereochemistry is important. We will try to understand that how we can name different stereoisomers. Right? We will also try to establish the understanding by which we can recognize the structures and what relationships they will have in terms of stereoisomers when they are present in similar sort of structures. And finally, we will talk a lot about chirality, what are chiral structures, draw mirror images and compare them with each other to again tell what is the relationship between those. Right? So first of all, to put in the perspective why we need to bother so much about stereochemistry. Because when connection is different, it is easy to tell that compounds will be different. But when even the connection is same, but their orientation in space is different, what difference can it make to the structure and chemical and physical properties? I think this will be a perfect example to see that. This is a molecule where we have glucose joined with each other in a fashion that this bond is equatorial from both sides. This is the structure of cellulose. While in the molecule starch, we have one bond of glucose as equatorial and other one is as axial. Right? So this is the only difference between these two molecules. Cellulose and starch both are polymers of glucose. But because of this one minor difference, this is what happens. Now we can digest one and cannot digest the other one. Their structure is changed, their chemical properties are changed, and their physical properties are changed. So that is why it is super important to understand stereochemistry, just like as we do for different connections. So when we talk about different connections, we are talking about constitutional isomers. When we only talk about the orientation in space, about the bonding, then we talk about stereoisomers. So technically speaking, cellulose and starch are stereoisomers of each other. And the only difference in them is that one bond, which we saw in the previous slide. So what difference does it make? That cellulose makes sheet-like structure and starch makes helix-like structure. So with just one bond, so much difference, right? But when we want to study stereochemistry, the most important point So chirality comes from, I don't know which language word, but it does mean, is it? Greek. Sure? I will quote Victor on this. I can't remember at the moment. But it doesn't matter. Yeah, it is a word in English as well now. It has been like inducted in English language as well. So chiral would mean handedness. Handedness, as the name suggests, has something to do with things which are different for left hand side and right hand side. Right, so if you have right hand and you put it in front of mirror, you would think that you are getting the image of left hand side. Right? But can you superimpose these two things on each other? It appears that you will, just like that, right? But consider that this is the front of the hand and this is the back of the hand. So when you are trying to superimpose them, they don't align. Right? It appears that they do, right? But you are missing the point that this is the front hand and this is the back of the hand. So right now, if we put the hands together, the front side will be like that. So technically it will be like, it should be like this to make it superimposable. So this is what handedness is. Just the example of gloves or socks. So socks is something which you can wear on both feet. Can you wear gloves on both hands? So right hand glove will not fit the left hand, and left hand will not fit the right hand. Unless they are ambidextrous, meaning that it doesn't matter. You can flip them and put your hand in there. The one we use in lab are ambidextrous. It says on the box that you don't need to worry about left and right glove. But if they are stitched tightly, then you wouldn't be able to fit your right hand in the left hand glove. Just an example. Handedness is chirality is the concept of handedness, technically speaking. Right? So an object would be called chiral when its mirror image is different from the original object. Or in stereochemistry terms, that when its mirror image is non-superimposable on the original object. Right? So the mirror image of a molecule will never be superimposed completely on its own molecule. That's what chirality is. The one example we saw for chirality is hand, right? Can you tell me an example of a thing? Let's just not say molecule right now. Hand is an example of chirality. So can you give me an example of an object which is not chiral? Meaning that the mirror image of that thing can be superimposed on the thing itself. The marble? Marble. The plain marble. Yes. Perfect. No problem. But if you put a marker pen ink on one side of the marble, then what? It will become chiral. Because then you will not be able to put it back on the marble itself. So another example would be just like chair, for example. It doesn't matter that you can just squeeze it in the mirror itself and it will align itself perfectly with the mirror image. If you would be able to do that, of course you are not. So why this deception happens that we are thinking that, well, it does superimpose, right? Because it just fits right on the other hand. This is an optical illusion because our mind is not being able to see the difference between the top side and the back side. Imagine that if you are able to see in the 3D, then it will be like this actually, right? And the image would be like this. So when you will take them closer, so this and that, they will come on the way of each other to become superimposable. Because right now you are probably only considering hands as 2D. That's why you are thinking that, well, why not? So if you put it in 3D, just like that, then they will not be superimposable. If you are to put it like this, then you see the thumbs, they don't match with each other. Now that you are trying to match these two. Now these two are matched, but the thumb is not matched. So that's the thing. Right? Thumbs are on the opposite side. Right, I think you get the point, right? Perfect. So chirality is basically having no symmetry at all. When we have any element of symmetry in the molecule, or let's just say object until now. I haven't touched on molecules part yet, right? So chirality in a thing is absence of symmetry, generally speaking. So symmetry has two elements. One is called plane of symmetry, other is called center of symmetry. And they are, as the name suggests, if there is a plane which can bisect the object in two equal parts, then we will say that this object has plane of symmetry. Or if there is a point in the center of the object which is equidistant from things at the opposite side, then that point would be called center of symmetry. Are you able to relay this point? So imagine that this sheet, this is the center, right? So this point, that point, equidistant from each other. This point, that point, equidistant from each other. So this would be the center of symmetry. While if we cut it like this, again, two equal parts. But if we cut it like this, then this part is not equal to that part because this part has this metal. And that part does not have this metal. So this is the plane of symmetry, and this is not the plane of symmetry. And then this would be the center of symmetry if we consider that that side is also same as this side, which we are not considering at the moment, right? So yeah, it does not have a center of symmetry. So any one element, either center of symmetry or plane of symmetry, if this is present in any object, then it cannot be chiral. So the term for the thing which cannot be chiral is achiral. Okay? So far, it's only trivia, and we are only talking about objects. You will see soon that how all this information is used in compounds. Here it is. So this is a molecule. What is it? 1,3-dimethyl cyclohexane, right? The molecule. Now this red line bisects the molecule in two equal parts. Isn't it? Also notice that the methyl group are actually cis because both of them are outside the plane. If one of them was inside, then we would not be able to have two equal parts. One of them would be outside and the other one would be inside. So since both of them are outside, so this molecule has a plane of symmetry. Are you able to see the difference, what I'm saying? Right? So this red line is the plane of symmetry, meaning that this is an example of achiral molecule. Another example of this molecule, right? The horizontal red line dissects the molecule in two equal parts. Correct? Another example. Now the example of center of symmetry is, this is what I was saying. So A is down there, A is up there. So technically opposite at the center point. C is up there, C is down there. Center of symmetry. An actual example would be this or this. So here it is above the plane. The opposite, same group, but below the plane. So we will have the center of symmetry right there. Does it make sense? Right? Any confusion? If you don't understand this, you will have hard time in next few slides. This is the foundation of stereochemistry. symmetry you have to understand. Point of symmetry or plane of symmetry. There are axes of symmetry as well in some molecules, but the key for us that they are not part of our symmetry. There are different types of stereoisomers which we will not cover in this part. Right. So when we talk about chiral carbon atom, because that's what we will be interested in mainly, that would simply mean that a carbon which is attached to 4 different groups. So since carbon in its single bonded form is tetrahedral, and if it has 4 different groups, then no matter how you rotate it, the mirror image will never be superimposable on the tetrahedral carbon, because the 2 groups are inside and outside the plane. So if you rotate them, then they will be opposite again. Right? You see this? That if these 2 fingers are the plane, then this is outside the plane, this is inside the plane. So if you keep this here and rotate it, then these groups become opposite of their mirror image. So that's why tetrahedral carbon, when it has all 4 different groups, it is a perfect example of chiral carbon. So when we say chiral carbon in this course, it will most of the times mean that we are talking about the carbon which is attached to 4 different groups. And it is also called asymmetrical carbon because no symmetry at all, right? So hence the name asymmetrical carbon. So its mirror image will be a different molecule. And that mirror image molecule and the parent molecule will be called enantiomers of each other. So this is the first example of stereoisomer in specificity. So enantiomers are stereoisomers which have mirror image relationship with each other. And this is how they will be to each other. They are just mirror images of each other, but they are 2 different molecules. Yeah? Right, yeah, so this is what I was saying. Achiral would be the thing which is superimposed on its mirror image. So meaning that the mirror image and the main object are technically same thing. It does not make any difference. Because apparently chair would be just squeezed into its mirror image right as it is. Right? So in terms of carbons, if any of the 2 groups are same, then we can say that that carbon will be achiral. Because now you can rotate it any way you want and it will be superimposable on its mirror image. It will not have that problem now, or that problem now about the thumbs. Because the 2 groups are same, let's say that the thumbs are same, then these 2 mirror images can be superimposed on each other, even if they are 3D, because we have taken out the non-matching parts, right? So this is what happens. If 2 of the groups are same, then you can simply rotate the molecule and this becomes that, right? So this is an example of achiral carbon, or any compounds which have achiral carbon would be achiral compounds. If you are only talking about, of course, one center. A molecule can have many achiral carbons and chiral carbons at the same time. So it's not always that if a molecule has an achiral carbon, then it would be called just achiral carbon. Depends on other centers as well. So we are talking about just one center at the moment, which is the black one. Right? Any question here? The rotation part, do you understand this? So this is the mirror image of, this is the mirror image of this molecule, right? So 3 are facing towards each other, 2 is away from each other. Now the mirror image is a different molecule. So you can do what? Hold it from here and just rotate it. So 3 goes this achiral carbon. Right, so why this is happening? Because now it has plane of symmetry. When the two groups are same, then this is the plane of symmetry. This plane, which is imaginary plane, is dividing the molecule in two equal halves. That is the definition of plane of symmetry, right? So when two groups are same at a carbon center and two groups are different, then the molecule will have plane of symmetry and therefore they will be achiral. Remember that to rule the molecule achiral, it needed to have those elements of symmetry, right? Plane of symmetry or center of symmetry. So when two groups are same, then we are actually having plane of symmetry in the structure, and therefore they will be achiral. Correct? Is this the repetition? Okay. I haven't moved to the next step yet. Right, so based on these chirality elements, the stereoisomers can be classified. Yeah, the other things you know already, right? Constitutional isomers, conformation, heteroisomers, don't need to put too much focus on it. What I want you to focus is on stereoisomers. So, stereoisomers could be when there is no chiral center in the molecule. We will see that the molecules which have no chiral center can still be stereochemically active or can have stereoisomers. And the example are cis and trans. So, E and Z or cis and trans are actually stereoisomers of each other. So they are called distereomers. Right? If there is chiral center in the molecule, then we can either have just one chiral center or we can have multiple chiral centers. So if the molecule has a chiral center and only one of that, then there would be enantiomers to each other. And if we have more than one, then they could be either achiral or again chiral. So if they are achiral, then they are called meso compounds. And if they are chiral, then again we have two possibilities. Meaning that if we have more than one chiral center, right? So if they are not mirror images of each other, then they are distereomers. But again, if they are mirror images of each other, then they would be enantiomers. So altogether there are three types of stereoisomers that we are interested in. Of course, there are other types as well, but these three are the ones which we are interested in. Number one, enantiomers. Number two, diastereomers. And number three, meso. Okay? And the definition is right there. So enantiomers are when they have mirror image relationship with each other. Diastereomers are when they don't have a mirror image relationship with each other. And meso is when they are achiral. So that's the definition of the three most important stereoisomers that we will be talking about. Heteroisomer is very niche, not part of our syllabus, forget about it. Conformation simply means the rotation of single bond. So when rotation of single bond impacts on the stereochemistry, then they become one of these three. When it does not impact, the molecules' bonds can rotate at normal temperature all the time. So the difference in their positioning is called conformation. Not important at all. Because all molecules, they are freely rotating through their bonds all the time. So these are the important types of stereoisomers that we will be looking at. So first is enantiomer, right? This is the molecule. This is its mirror image. What you notice is this carbon is asymmetrical carbon. Why? Because 1, 2, 3, 4. All 4 different groups. Again, identifies with the asterisk, 4 different groups. The relationship between these two is what? That they are mirror images of each other. say that they are mirror images of each other while they were chiral, that would mean that they are enantiomers. Right? So a chiral molecule having its mirror image would always be enantiomer of the mirror image. So this is the definition. The compounds that are non-superimposable mirror images are enantiomers. Okay? Are you able to see the difference between two mirror images of each other while both of them are chiral? So they would always be what? Enantiomers. Right? And this is just a classic example. Having an asymmetrical carbon, it tells clearly that these two are mirror images. In some cases, it's difficult to see if they are really mirror images, which we will see later. But this is just a simple example. Why? Because chirality is easy to identify here. Because it is an asymmetrical carbon, meaning that it is attached to 4 different groups, right? Right, what about in this case? So it's a bit difficult to see now. Because the whole structure is attached to it. In previous case, we were only talking about the compound which has one chiral center. This one also has one chiral center only, but because of the structure, maybe your eye deceives you to see that yes, these two are actually the mirror images of each other. Are you able to see that? This one is inside. The mirror image, this one is outside. So they are facing towards each other. So what was outside is appeared to be as inside, if the mirror was there. Right? So one of them is plus and other one is minus. We will talk about plus minus later. One of them is S, other one is R. We will talk about R and S later. But what I'm trying to show here is that because of the difference in their stereochemistry, they have different chemical and physical properties. So much that this is the principal compound of caraway seed and this is the principal compound of spearmint oil, which gives them their characteristic fragrance. So you would imagine that spearmint fragrance would be totally different from caraway fragrance, right? And why we are able to identify them with our nose? That yes, this is spearmint and this is caraway. Because our nose receptors are also chiral. So only a chiral environment can identify the difference between chiral molecules. If we are able to tell the difference in smell of these two compounds, this suggests that the receptor molecules in our nose, which are responsible for the identification of smell, can tell that which one of them is what. Right? Are you able to understand this point? So generally, all the biomolecules that are part of our different systems, such as carbohydrates, amino acids, lipids in some cases, but yeah, amino acids and carbohydrates, all of them are chiral molecules. So all the enzymes that we have coming from proteins, most of the biomolecules, the point is chiral, right? Why this is important? Because specific receptors will have specific lock and key models for specific enantiomer or specific chiral molecule. If you talk about enantiomers, that means that if the structure is exactly like this, then it will fit. If it's not like that, then it will not fit properly. And then imagine that if it's the structure of a drug, and if this is the structure of the receptor, then you lose the potency of that drug so much. Even though they are just isomers of each other, they are just differing in the orientation at one of the carbons or one of the groups which is attached to that carbon. With that small difference in stereochemistry, their potency now is no more. And in some cases, it can impact it negatively, which we will see. I think I had put the example. Yes, thalidomide, but where is it? Epinephrine, again, another example. If the right isomer is not used, then it will not give you the required effect. But thalidomide was an actual example. This happened in Germany, if I'm not mistaken. That the right isomer was S isomer, which was a sedative. But people mistakenly used the wrong isomer, which was the R isomer. So you see the difference? Not that much. Only here, the orientation. Here, this group is outside the plane. Here, this group is inside the plane. And this molecule had teratogenic activities, and a lot of children suffered because of this small mistake in Germany in 1950s, if I'm not mistaken. This is a very famous case about the importance of stereochemistry. It is also important to note that we actually need the right isomer, right stereoisomer, or right enantiomer. Since we are only talking about enantiomers, so I can say that enantiomers were more contaminated. In cases when you don't use the right isomer, but you use them in mixture, and if the other isomer had, adverse effect like this also suggests that we only need the exact isomer which is required for that activity. And we saw previously that how having different isomer can have totally different activities altogether, right? Yes, I think this is about the thalidomide, right? Yes. So that was I was saying. So a mixture which is at equal concentration of both the enantiomers is called racemic mixture. So imagine that you are doing a synthesis, a reaction in which a chiral center is involved. So if you don't control the stereochemistry of your product, then you will get both the enantiomers in equal volume or equal concentration. So that mixture of equal concentration of enantiomers is definitely called a racemic mixture. Okay? So in those reactions, if we need the specific enantiomer, then we will need to separate the isomers by doing certain separation techniques, such as we did it in our last practical. Chromatography. We have chiral columns for chromatography by which you can easily isolate enantiomers. Not that easily though. I mean, as opposed to non-chiral molecules, it is a bit difficult and more expensive, of course. But yes, we do have chiral silica, which can help in the separation of the racemic mixture, or the component of the racemic mixture, I should say, the enantiomer. So the separation of enantiomers is called resolution. So these are the two terms which you may need to remember, might be important for the MCQs of your exam paper. The racemic mixture is the equi-concentration mixture of the two enantiomers. And resolution is the process by which you can isolate the enantiomers from the racemic mixture. Right? Right, this brings me probably to the final topic for today, which is about how do we name these enantiomers. Right, so the all other IUPAC rules are still applied, but you need to identify one enantiomer from the other enantiomer based on these letters, I and S, as per the IUPAC convention. So I need your attention for this. As E and Z was important for your exam, same is R and S. You will definitely have a question about R and S in your exam. Right, so one of the enantiomer is called R and the other one is called S, as per the IUPAC rule. How can we identify which one is R, which one is S? As per the CIP conventions again. You remember the CIP convention? Where we give priority to the next connecting atom based on their atomic number, as we did for E and Z alkenes. Same rules. But what are those rules? Right, of course, if we give the IUPAC name, then both of them will be same name. So we have to specify that which enantiomer are we talking about. So we do that by putting R or S. R simply means rectus, and if I'm not mistaken, that's from German again. And S, I think, means sinister, which means left hand side, or the one which rotates to left hand side. And rectus, the one which rotates to right hand side. How it works, we'll see that. This is how it works. Right? Again, CIP conventions. So based on atomic number, you will have to give priority to all the 4 different groups which are present on that chiral carbon, and then you will look at their rotation from 1 to 2 and 2 to 3. If your rotation from 1 to 3 is clockwise, provided that the least priority group is behind the plane. Hear my words carefully. First thing you need to do is to see that if your lowest priority group is behind the plane or not. If it is, then you have to look at the rotation from 1 to 2 and 2 to 3, and if that rotation is clockwise, your molecule would be R. And if your rotation is anti-clockwise, then your molecule would be S. This is when your number 4 is already behind the plane. So this is the prerequisite. You have to look at priority 4 group. It must be behind the plane to tell R apart from S. This is case 1. When number 4 is already behind the plane. Right? And then you already know, right, how to give priority. These are the 4 groups. So methyl, hydrogen, nitrogen, fluorine. Fluorine takes priority 1, nitrogen takes 2, carbon takes 3, hydrogen takes 4. Hydrogen is number 4, it must be behind the plane. It is already behind the plane. No problem, we don't have to do anything. Now you only need to tell the rotation from 1 to 2, 2 to 3. So 1 to 2 to 3. This is anti-clockwise. Right? So this would make this enantiomer S. Okay? Easy, right? Right. So yeah, this is the same thing that I've been saying. 1 to 2, 2 to 3, when 4 is behind, is clockwise. So R, if it's anti-clockwise, then S. So the first case was what? When hydrogen is already given in question at behind the plane. Right, this is just the repetition. So what happens when hydrogen is above the plane? So of course, there is a logical way to do it and there's a trick to it. So I'll tell you both. When we have hydrogen, or not to say hydrogen because it's hydrogen here, but when priority 4 group is above the plane, at the opposite of where it is supposed to be. Right? It is supposed to be always behind the plane. When it is the case, then you can do, logically speaking, hold one side and rotate the molecule to send it behind the plane. Can you do that? So I am holding it here, and now I am rotating this side. So hydrogen which is above the plane now goes behind the plane. The behind the plane would come on the plane. So it's like a fan, right? There's no fan here. Okay. Right.
So does it rotate clockwise or clockwise?
Both ways you can do, no problem. You will do in a way that you send hydrogen behind the plane. Right? So if this is hydrogen which goes above the plane, if you want to send it behind the plane, you can do this or that. Right? It doesn't matter, you can do any of the rotation. The purpose is to send hydrogen behind the plane. If this is the plane and this is out of the plane at the moment, right? So to send it backwards, you can, do that or do that. It does not make any difference. If you are able to imagine this, that's wonderful. But some people are not so able to see the things in imagination. So I have a trick for them. Right? And that trick is that if hydrogen is opposite from where it is supposed to be, you don't have to do anything. Just tell the rotation and then reverse your answer. You will always get it right. Okay, so number 1, number 2, number 3, which is anti-clockwise at the moment, which should be S. But since hydrogen is opposite, so you'll have to reverse your answer, which will make this molecule R. Forget about the rotation and everything. I mean, rotating the molecule and all. Right? This is the trick. Always you will get the right answer. Does this make sense? There at the back. Super important. Right. The third and final case would be when number 4 is on the plane. It's neither above the plane or behind the plane, but it is right on the money. Okay, what one will this be? So hydrogen is already behind the plane. Which one is 1? This, right? Which one is 2? And then this one is 3. So 1 to 2 and 2 to 3 is anti-clockwise. Which means this molecule is S because of course hydrogen is behind. Right? Correct? Now what happens here? Hydrogen is on the plane. So again, if you are good with rotation, perfect. You can send it behind the plane. But if you are not good with rotations and imagining, then the trick is that you replace hydrogen with whatever is behind the plane. Right? So hydrogen is here and this group is behind the plane. Just replace them. Put methyl here and hydrogen here. Now hydrogen is behind the plane, right? Since we have just switched them. We are not allowed to do it, but for the sake of getting the right answer, you can do it. And then do your rotation, imagining that hydrogen is already behind the plane because you just switched them. And still reverse your answer. That will give you the correct answer. Right? So number 1 is what? Bromine, right? Number 2 is chlorine. Number 3 is methyl. So methyl goes there, hydrogen goes here. Hydrogen is fixed now. Right? But methyl is here now. So 1, 2, 3. Clockwise. Which should be R. But I asked you to reverse your answer because you did this illegal thing of, switching them. So this will give you the right answer. Right? Okay? Awesome. new or we can call it a day? Of course. Alright then. I will see you in
Kaya sa point tayo.
lab. Right? There are no tutorials this week. That will be Thursday and Friday.